Hi, everybody. Let's take a look together at your practice exam for the content covering sections 5.2 through 6.7. So you'll see I pick up with section 5.2 here in the beginning, and several of the problems in that section had us to use the cosine and sine addition formulas. And several of the problems ask us to do verifications similar to the section 5.1 verifications, which were beautiful. Uh, the ones in 5.2, the verifications comes as a direct use of the sum or addition formula. So you'll notice the formulas that I give you on the test, you do not have to have the angle sum difference formulas memorized for the cosine and sine function. And I won't even give you the tangent sum or difference formula on the test. There's no problems with it. But you just have to be able to use these formulas. So the first problem where I ask you to verify that the cosine of pi plus x is equal to the negative cosine of x, notice all you have to do here is say, well, okay, the cosine of pi plus x, use your cosine sum formula on it. It says it's the cosine of the first portion, cosine pi, plus cosine of the second part of the sum inside the angle, cosine of x. So I get cosine pi, cosine x, change the sign, minus sine pi, sine x. That's always going to work. It's just a direct use of the formula. Then you have to be able to evaluate. Well, we know that the cosine at pi, the x component on the unit circle at that point is -1. So I'll get the cosine of pi is -1 times the cosine of x. We know that the sine of pi is 0 times the sine of x. So I'll just get -1 times the cosine of x minus 0. We know that's the negative cosine of x. That's precisely what we were trying to show. So at that point, you put the little check over the equal sign and say verified. So we're done with the first problem there. Now, for the second problem, if we're looking at it, it says use the double angle identity to verify the fourth power of the cosine minus the fourth power of the sine. So cosine fourth x minus sine fourth x is equal to the cosine of the double angle of 2x. So cosine of 2x. Okay. Now, I already know that the cosine of 2x formula, I'm going to have three different varieties of that formula. I know cosine of 2 alpha is cosine squared alpha minus sine squared alpha. Cosine of 2 alpha is 2 cosine squared alpha minus 1, or it's 1 minus 2 sine squared alpha. Since I see the other side is cosine to the fourth minus sine to the fourth, it's in terms of cosine and sine. I know the identity that's going to be helpful here is the first one. Cosine of 2 alpha is cosine squared alpha minus sine squared alpha. So now, notice, I go to my work page. I'm working with the left-hand side of that expression because it looked more complicated. So I can say, well, I know it's a difference of two squares, a fourth power minus a fourth power. So I can say, well, then it's going to be the square root of the first term plus the square root of the second term times the square root of the first term minus the square root of the second term. That gives me cosine squared x plus sine squared x times cosine squared x minus sine squared x. But then this problem really simplifies easily because by the Pythagorean identity, we know that cosine squared x plus sine squared x is just 1. So then that leaves us 1 times cosine squared x minus sine squared x. And then you can say, by identity, we know cosine squared x minus sine squared x is the cosine of the double angle 2x. That's just the very first part of your identity formula right here. So once you get down to the other side of the identity, of course, this is equal to that. So verified. And the next one, it's giving us a function with a bunch of different sums and differences going on within the angle. Notice I have to verify the sine of x plus y plus the sine of x minus y all over the cosine of x plus y plus the cosine of x minus y. And we're supposed to show that this is equal to the tangent of x, which I'm thinking in the back of my mind, well, of course, that's sine x over cosine x. So I need to show the numerator simplifies down to sine x, the denominator simplifies down to cosine x. I clearly work with the left-hand side in this verification problem because it's the more complicated side. So working with that left-hand side, I'm just using the sum and difference formulas. Sine of x plus y is sine x cosine y plus cosine x sine y, plus the sine of x minus y. That's going to be the sine of x cosine y minus the cosine of x sine y. All of those, that's just formulas straight from your test. I hope you don't need to use the formula on the test because these are pretty easy, but it's there in case you forget. Cosine of x plus y is cosine x cosine y minus sine x sine y. And then the cosine of x minus the sine of y is cosine x cosine y, change the sign, plus sine x sine y. So now, whenever I start trying to simplify, I can see that there's terms in the numerator that cancel. I'll have a plus cosine x sine y minus cosine x sine y. The second and fourth term cancel, leaves me with these two, which are the same. Sine x cosine y plus sine x cosine y gives me 2 sine x cosine y. Similarly, in your denominator, you can see the second and fourth term cancel, but then the first and third term, cosine x cosine y plus cosine x cosine y, gives me 2 cosine x cosine y. At this point, we can see that the 2's cancel in the numerator and denominator, and the factor of cosine y's cancel in the numerator and denominator, leaving us sine x over cosine y, which we know is the tangent of x, and that's precisely what we were trying to prove. So at that point, you know it is verified. So the first 3 problems, verification problems. Sadly, no verification problems after that, though. Number 4, and this is an extremely important problem. It's very, very important to be able to reduce the power of trigonometric functions. Most notably, I can think of when I teach a Calculus 2 class, we have to do things like integrate the sine to the 4th power of x. It is absolutely impossible to integrate the 4th power of the sine of x if you don't know how to rewrite it in terms of cosines to the 1st power. So this, you might call it a little trick that we're doing here, is extremely important in the future. So you say, well, okay, how do we reduce down powers? You use the power reduction formula. You know that the sine squared alpha is equal to 1 minus the cosine of twice alpha divided by 2. So I can say, well, all right, using that formula within this problem, I know sine to the 4th is nothing more than sine squared quantity squared. Now, that sine squared on the inside, that's what I'm using my formula. I know it's equal to 1 minus the cosine of twice the angle divided by 2. But now that group is being squared, so I square that group. At this point, what I did is I just said, well, I know that that 2 is in the denominator. When I square it, it'll be 4. Instead of dividing by 4, I preferred to just factor out a factor of 1/4. So then I had 1/4 times the group, 1 minus the cosine of 2x, quantity squared. 1 minus cosine 2x times 1 minus cosine 2x gives me 1 minus 2 cosine 2x, and then it would be the cosine of 2x times the cosine of 2x for plus cosine squared 2x. So now I can say, well, all right, you reduced it down from the 4th power into this expression, but now after you squared that out, we still have a 2nd power of cosine. But the problem explicitly says to reduce it down to a single power of cosine. So you say, okay, you're not done. How do you do it now? You use the power reduction formula for your cosine. So I rewrote this as 1/4, and I just left the first 2 terms alone inside the group. 1/4 times the group 1 minus 2 cosine 2x. And then I had plus, and now I know that cosine squared 2x by formula is 1 plus. The only difference in our power reductions for sine and cosine If it's sine, it's 1 minus the cosine of twice the angle. If it's cosine, it's 1 plus the cosine of twice the angle. Well, twice the angle this time is going to be 4x. Please keep in mind, you always divide by 2. A common mistake students will do here is they'll say, well, if I put a 4x here, should there be a 4 in the denominator? No, it's 1 plus the cosine of twice the angle divided by 2. Now, I'm just simplifying. Final answer here, I'll leave the factor of 1/4 out in front. On the inside, I'm going to have common constants. I'll have a 1 plus a 1/2. Well, 1 plus 1/2 is 3/2. Then I'll have minus 2 cosine of 2x, and then my last term is going to be the cosine of 4x divided by 2. I preferred to write that as plus 1/2 cosine 4x. Final answer. You could have distributed in the 1/4, but there's no reason to do that. It's kind of better to leave it factored out. If you wanted a beautifully factored answer, you might also factor out an additional factor of 1/2 and have a 1/8 out there. And then the inside would be 3 minus 4 cosine 2x plus the cosine of 4x. But this is fine as it is. I'm not going to care about how you choose to factor or not factor that answer. All I need is an answer with only linear powers of cosine. We have it. Now for the next problem, it's asking us to write the exact value of the sine of 105 using the angle sum formula. Okay. So the sine of 105 degrees, all you need to do is think of some common angles that you're familiar with. Remember, that's just 30, 60, 30, 45, 60, 90. So some of those values that add up to 105, and you really don't have a lot of choices here. 60 and 45 is 105. So I'll stick with those. And in fact, I think this is the only choice if you want to use angle sum. So I'll say, okay, sine of 60 degrees plus 45 degrees is the sine of 105. But now my sine sum formula tells me that the sine of 60 plus 45 is sine 60 cosine 45 plus the cosine of 60 sine of 45. Now I want an exact answer, so we'll just say, well, we know the sine function at 60 degrees. That's 2/3 of the way through quadrant 1. The y component on the unit circle at that point is the square root of 3/2. Cosine 45, that's midway through quadrant 1. Cosine is square root of 2/2. Cosine of 60 is 1/2. And of course, the sine of 60 is also the square root of 2/2, just like the cosine is. So now at this point, you simplify. I saw that I was going to have a common denominator in each of the fractions of 4. So then I just combined my numerator. I'll have the root of 6 plus the root of 2 all over 4. Please keep in mind, you cannot combine the root of 6 and the root of 2. So the only way you can ever add square roots is if the exact same term is on the inside. And then at that point, you just add their coefficients. But in this case, I'd leave it as that. Now, you can always check your answers on problems like this. Even though I want an exact answer, you could go into your calculator and say, well, all right, the answer he is getting here, I can go math fraction. We have the square root of 6, and then I have plus the square root of 2 divided by 4. So the answer I'm getting for the sine of 105 degrees, 0.9659. All I would have to do is make sure my calculator is in degree mode, and it is, and say the sine of 105 degrees, it better be 0.965925826 or we will not have a test. Boom. But it is. So we are having a test. And you say, well, that's a great way to check your answer. I know, right? Now, for the next problem, it has 3 parts. I thought each part was not important enough to create its own problem. So it has parts A, B, and C. It's asking us to find the exact values of the following expressions using the double and half angle formulas. So please notice, guys, I'm not trying to be deceptive about when and what formulas to use. I'm being pretty clear cut here. Number 4, use the power reduction formula. Number 5, use the angle sum formula. 1, 2, and 3, you used your sum difference identities. Now in number 6, we're using the double and half angle formulas. So you say, well, all right, the double and half angle formulas. The double angle formulas right here, the half angle formulas right here. And if I don't put a half angle formula on the test, like the tangent of u over 2, that just means it's not on the test, so you don't need it. Now, when I look at number 6, and it's asking me to find the exact value, instantly you look at it and say, well, I don't know what the sine of pi over 8 and the cosine of pi over 8 is. No, that's exactly half of the angle you do know. You do know what the sine of pi over 4 and the cosine of pi over 4 is. So you'd say, well, okay, look over here. Boom, ding, 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 ding. I know 2 sine alpha cosine alpha is the sine of twice that angle. So I can say, well, then the sine of 2 pi over 8 cosine pi over 8, that'd be the same thing as the sine of 2 times pi over 8. Absolutely. That's all you do. You say 2 sine pi over 8 cosine pi over 8 is the sine of 2 times pi over 8. Well, that's the sine of pi over 4. And then we know that the sine function at pi over 4, that's midway through quadrant 1, that's the square root of 2 over 2. That's what we do. Now, just as I used the double angle formula on this, I look at the next one and say, well, I'm going to use the double angle formula again, because I don't know what the tangent of 15 degrees is. I do know what the tangent of 30 degrees is. So notice now, if I go to the double angle formula, it says 2 tangent alpha over 1 minus tangent squared alpha. That's the tangent of 2 times alpha. So the problem I'm giving you here, 2 tangent 15 degrees over 1 minus tangent squared 15, that fits this perfectly. So you just got to find the formula that fits what I'm giving you over here. And you say, well, I'm just working backwards in this formula from the right-hand side to the left. So the 2 tangent of 15 degrees over 1 minus tangent squared of 15 degrees, that's going to equal the tangent of 2 times 15 degrees. So now I go back to my work page and I can say all of that's just going to equal the tangent of 2 times 15 degrees, which I know is the tangent of 30 degrees. And now when I think tangent of 30 degrees, I should be thinking, well, it's the sine of 30. The sine function at 30 degrees is 1/2 divided by the cosine of 30. Well, that's the square root of 3 over 2. 1/2 divided by the root of 3 over 2 is just going to be 1 over the root of 3. And I would be fine with that answer. You could leave it like that. Or if you're one of those that likes to rationalize, I have no preference. I'm perfectly fine with this answer. But if you wanted to rationalize, you'd multiply by the root of 3 over 3 and get the root of 3 over 3. Final answer either way. Now, for the last one, I gave you the cosine of 5 pi over 12. And you say, well, all right, I don't know what the cosine of 5 pi over 12 is. However, I do know what the cosine of 5 pi over 6 is. 5 pi over 6, that's pi over 6 radians short of pi. My cosine at that point is going to be the negative square root of 3 over 2. So I can rewrite the cosine of 5 pi over 12. It's exactly half of the angle I do know. So I'll say I'll rewrite this as the cosine of 5 pi over 6 divided by 2. And I know that that would equal my cosine of 5 pi over 12. But now in this format, it's fit perfectly to use this half angle identity. Now in the half angle identity, the formula does not tell you whether your answer should be positive or negative, but we should be sure here. The cosine of 5 pi over 12, that's going to be less than pi over 2, so we're still in quadrant 1. Since we're still in quadrant 1, we know our cosine function is going to be positive. So you'll see, first thing I did here is say, well, my answer is going to be positive, and then it's going to be the square root of 1 plus cosine of 5 pi over 6 all over 2. Now I plug in the cosine of 5 pi over 6, negative square root of 3 over 2. I simplify this compound fraction by multiplying by 2 over 2 on the inside. Of course, that gives me a 4 in the denominator. In the numerator, it would give me 2 minus the root of 3. So now I can say, well, All right, 2 minus the root of 3 in that numerator all over 4, but it's all inside of a square root. The numerator doesn't simplify, so I just have to say the square root of 2 minus the root of 3. Of course, the denominator, the square root of 4 is 2, so we get our final answer down there. Now, for the first time, you might want to check this one just to be sure you're on the right side, so I will. And I could say, well, all right, if I were checking this time I need to be in radian mode. Please make sure you're in the right mode if you're wanting to use your calculator to check these. And we say, well, this is the cosine of 5 pi divided by 12. The decimal answer I should be getting. Now, please keep in mind, if you put this answer on the test, I give you no credit whatsoever because I'm expecting an exact answer. No matter how many decimal places you're putting out, that's not an exact answer. But now to check our exact answer, you could just say, well, the answer that we got was the square root of 2 minus the square root of 3 inside of that root. I'll go outside the root and divide by 2. This better be 0.2588. And it is, so that's great. So now, first 6 problems done. What about the next one here? And I'll go to my second page of the work too. It took me 4 pages to do the work for this test. The 7th problem here says find the exact value of the following quantities given that the sine of u is equal to 4/5 and the secant of v is -3. And then you're told that both angles u and v are in quadrant 2. Okay. So we're supposed to find the cosine of the difference of u and v, the sine of 2v, and the cosine of u over 2. All right, let's go to my work page. So given that the sine of u was 4/5 and that u was in quadrant 2, instantly when you're told an angle's in quadrant 2, you can kind of draw it out. Remember, u is the angle between the hypotenuse and the x-axis here. So you can say the sine of u is 4/5. So opposite over hypotenuse, 4/5. Now, since this triangle is in quadrant 2, you know the x components moving to the left has to be negative. So I just recognized it's one of our special case triangles. It's a 3, 4, 5 triangle, but of course the x component's negative, so it's -3. You could have also used Pythagorean theorem if you wanted, but on this one, it should be obvious. It's a special case triangle. It's a 3, 4, 5 triangle. But again, Pythagorean theorem would work to find that. You just have to understand the x component's negative. Now, over here, if I told you that v is also in quadrant 2, again, I drew an angle in quadrant 2. The v is the angle between the hypotenuse and the x-axis. And now in labeling the sides, we knew that the secant of v was -3. Well, I just thought of it as, well, then the cosine is the reciprocal of that. It's -1/3. Now, I know that the hypotenuse cannot be negative. So when I say the cosine is equal to adjacent over hypotenuse, I know it's the adjacent side that's the negative. So I put -1 for the x component, then since it's moving to the left. And then the hypotenuse is 3. Now, the other leg is always the square root of the hypotenuse squared minus the other leg squared. So I get 3 squared minus 1 squared. And keep in mind, it doesn't matter whether you say minus a -1 squared or minus a 1 squared. You get the same answer. It's going to be the square root of 8. And the square root of 8 simplifies better to 2 on the root of 2, since it's the square root of 4 times the square root of 2. Now, I have my triangle for v and u defined. I should be able to go in and answer these questions. Part A, the cosine of the difference of u and v. Well, I know by formula, it's cosine u sine v plus the sine of u times the sine of v. Now, the cosine of u, well, cosine of u, I just go to u and I can say, oh, well, cosine of u was -3/5, done. Cosine v, that was my -1/3. That was part of the given. Plus the sine of u. Well, the sine of u is going to be 4/5 times the sine of v. And I know that the sine of v over here is my opposite over hypotenuse, 2 on the root of 2/3. At that point, I realized I would get a common denominator of 15 in both fractions. So I said, well, then let's just combine our numerators. We'll have -3 times -1 for my +3 over here. And then I have my 4 times the 2 on the root of 2 for my +8 on the root of 2. 3 plus 8 on the root of 2, all over 15, final answer. Now, if we take our sine of 2 times v and say, well, okay, the sine of 2 times v, if I take double this angle and try to take the sine of it, I already know my answer better be negative, because if you double any angle in quadrant 2, you know you're going to be down here, and the y component is going to be negative. So no surprise that I get a negative. It had to be. But now your sine of 2v by formula, it's your double angle formula, we get that the sine of 2 alpha is 2 sine alpha cosine alpha. So it's just a matter of using that 2 sine v cosine v. I can say, well, 2 times the sine of v, 2 on the root of 2 over 3, times the cosine of v, my -1/3. When I multiply that out, I know I'll have a denominator of 9. My numerator is going to be 4 on the root of 2 times -1. So I get -4 root of 2 all over 9. Final answer. For my last one, I asked you to do the cosine of u over 2. So I knew automatically if u is an angle in quadrant 2 and I took half of that, then u over 2 is going to be an angle in quadrant 1. So I need to understand from the very beginning of this problem that my answer is going to be positive, because it has to be in quadrant 1. Half of any angle in quadrant 2 is going to be an angle in quadrant 1. The cosine's positive there. Now, after I determine that, then I just go in and say, well, my formula says it's the square root of 1 plus cosine u over 2. 1 plus the cosine of u, that's going to be 1 plus -3/5 all over 2. I simplified that by multiplying by 5 over 5. This gave me a numerator of 5 minus 3 and a denominator of 10. Now, clearly that inside is going to reduce down to 2 over 10, which I just thought of, well, that's going to reduce down to 1/5, and the square root of 1 is 1, and then the square root of 5 doesn't simplify. So I would have been happy with 1 over the root of 5. For those of you that like to rationalize, another answer would be the square root of 5 over 5. Notice I did not say a better answer would be that. I have no preference between those two. It's whatever you want to do. It's fine with me. Now, the next problem, and I put a problem like this on our last test too. I'm revisiting it here because, again, this is an extremely important type of problem. In the future, you'll be asked to integrate expressions like this, and you cannot integrate that expression if you cannot rewrite it as an algebraic expression first. So I give you the cosine of the inverse sine of 1 over x. What you're supposed to remember here is that any inverse trigonometric function is just an angle. Since that fact, I can go ahead and just say, well, all right, how about I call that angle theta? So I just said the cosine of the inverse sine, same thing as the cosine of theta, where I have allowed theta to represent the inverse sine of 1 plus x. Now, if that's the case, then I can say, well, then I should be able to take the sine of both sides of this expression and say the sine of theta would equal 1 plus x, because sine and inverse cosine would cancel each other out. Now, since I know sine is equal to the opposite over the hypotenuse within a right triangle, then the sine of theta, instead of just putting 1 plus x, it's more helpful to put it as equal to 1 plus x over 1. Now, inside of a right triangle, I know the side of the triangle opposite theta has to be 1 plus x. I know the hypotenuse has to be 1. Now, that makes this other side a bit tricky here, because you're used to having clearly the hypotenuse larger than this side, and it is in this case too. It's just that in this case, the x component would have to be negative. So I can say, well, all right, how do I solve for the other leg? It's always the square root of the hypotenuse squared minus the other leg squared. So I showed that as the square root of 1 squared minus the group 1 plus x squared. Now, to simplify that out, I left my 1 squared as 1 and then minus that group 1 plus x quantity squared. A lot of students make the mistake and say, oh, that's 1 plus x squared. No, it's not. Any binomial squared is always a trinomial. 1 plus x times 1 plus x would give me 1 plus 2x plus x squared. Now I need to remember I'm subtracting that whole group. So I can see the ones will cancel out, but then I'll be left with a minus 2x and a minus x squared. So I get the square root of negative 2x minus x squared. That's the remaining adjacent side. So now I go back to my problem and say, well, all right, what do I want with respect to angle theta? I want the cosine of angle theta, which would be adjacent over hypotenuse. That's this answer divided by the hypotenuse of 1, which obviously doesn't even need to be there. Our final answer is just the square root of negative 2x minus x squared. Now, for number 9, I gave, it looks like 3 small problems within one. Let's see the actual way it's written on the test. It says determine the exact value again of the inverse sine of the negative square root of 3 over 2, the sine of the inverse cosine of 5/8, and then the inverse tangent of the tangent of 5 over 8. Okay, so the inverse sine of the negative square root of 3 over 2. First of all, you need to remember the sine function must be restricted to be from negative pi over 2 to pi over 2 in order for the inverse sine to exist. So whenever I'm thinking, okay, the answer for the inverse sine of the negative square root of 3 over 2, I should be thinking, when is my sine function negative square root of 3 over 2? And if I'm just thinking about that, I can say, well, that's true at 4 pi over 3 and 5 pi over 3. Neither one of those is going to be the answer for the inverse sine. Now it's going to be a coterminal angle to the angle at 5 pi over 3. But because the sine function has to be restricted from negative pi over 2 to pi over 2, the only value in that region in which the sine function is the negative square root of 3 over 2 is negative pi over the root of 3. So you say, okay, that's going to be the inverse sine of the negative square root of 3 over 2. For every input, there must be exactly one output. So please don't say, or 4 pi over 3. That's not correct. It's only that one answer. Now, for the next one, the sine of the inverse cosine of 5 over 8. This is actually more like the preceding problem, number 8. Anytime you have that inverse function on the inside, you can say, well, that's just going to be an angle, and I can find out information about that angle. Theta is the inverse cosine of 5 over 8, so the cosine of theta is 5 over 8. That means within a right triangle, the side adjacent to theta is 5, and the hypotenuse is 8, since cosine is adjacent over hypotenuse. Now that means your other side of the triangle, the opposite side, would have to be the square root of the hypotenuse squared minus this leg squared. 64 minus 25 is 39. I get that my other side is the square root of 39. So now the sine of the inverse cosine of 5 over 8 is equivalent to the sine of theta. Well, the sine of theta would be opposite over hypotenuse, the root of 39 over 8. That answer would be great. Now, again, the next one, I'm trying to trick you. You'd say, well, all right, the inverse tangent and the tangent, don't they just cancel and give you what's inside? Nope. The answer to this problem is not 5 pi over 4, and I need you to understand why. Similar to the inverse sine function, the inverse tangent function is only capable of giving you an answer between negative pi over 2 and pi over 2. The only difference, the inverse sine can equal negative pi over 2 and pi over 2. The inverse tangent can only give you values in between these. It's undefined at negative pi over 2 and pi over 2. So as soon as you see this, you should automatically say, I cannot give an answer of 5 pi over 4. So here's what you're supposed to do. You're supposed to think about it and say, well, find out what the tangent of 5 pi over 4 is. 5 pi over 4 is right here on your unit circle. At that point, your sine and cosine are both the negative square root of 2 over 2. So you can say, well, I know that the tangent, and I have a typo here, the tangent is not negative 1 there. Ooh, John, it's a positive 1. So I can say, well, the tangent at 5 pi over 4, since the sine and cosine are both the negative square root of 2 over 2, I know that the tangent at 5 pi over 4 is positive 1. So then the inverse tangent, it's asking you, I need to find the value on the tangent function in which the tangent is equal to 1. And you could say, well, that's going to be at positive pi over 4. I made an error on this problem. Boo for me. It's up here at positive pi over 4 because I know the tangent up here is equal to 1. The tangent of negative pi over 4 is equal to negative 1, since the sine and cosine are opposite signs there. So I will fix that and make sure I post the corrected version online. That's bad. Up next, two easy problems. I didn't like these, but I wanted to make sure I at least gave you a couple of problems, since you had a section where we had product to sum and sum to product. So number 10, obviously you have a product. You need to rewrite it as a sum. So it says, write the product cosine 5x sine 4x as a sum or difference. So you say, all right, I'm doing a product to sum. Well, here's my sum to product to sum. I'm going to be using one of these three formulas here. And it's easy to figure out which one. We have a cosine times a sine. So you can say, well, cosine times the sine. That's my third formula. Cosine alpha sine beta is equal to 1/2 sine the sum of the angles minus sine the difference of the angles. So I just apply that formula right here and say cosine 5x sine 4x is going to be 1/2 the sine the sum of the angles minus the sine the difference of the angles. Now, the sum of the angles gives me 9x, the difference of the angles, just 1x. Final answer, 1/2 times the group, sine 9x minus the sine of x. And then for my final problem here, number 11, or at least final problem on this sheet, I get the cosine of 195 degrees plus the cosine of 105 degrees. So then whenever I'm simplifying that out, I'll say, well, I know it has to be a sum to a product formula. That's what I'm looking for, because I don't know what the cosine of 195 and the cosine of 105 are. And I need to find the exact value, so the calculator doesn't really help since I'm trying to find an exact value. But the sum to product formulas will help. Notice if I have a cosine plus a cosine, it's saying that that is equal to 2 times the cosine, the sum of the angles divided by 2, times the cosine, the difference in the angles divided by 2. Okay, apply that to formula, and you'll say 2 cosine 195 plus 105 over 2 times the cosine of 195 minus 105 divided by 2. And in the first one, you'll get 300 divided by 2. That gives me the cosine of 150. The second one, 195 minus 105, that gives you 90 degrees in the numerator. 90 divided by 2 is 45. Whenever you work this problem, you know that you need to have it to simplify to be angles that we should be familiar with, since you're supposed to find an exact value. The cosine at 150 degrees, same thing as cosine 5 pi over 6. It's negative square root of 3 over 2. Cosine 45 degrees, square root of 2 over 2. So then we just multiply 2 times negative square root of 3 over 2 times the square root of 2 over 2. And we're going to get the negative root of 6 all over 2. Final answer there.